Moving on to week 5, we'll be talking about week 5.1 today, which is called, I think, the consequences of the rank nullity theorem, but that is just the meaning of another theorem. So we'll be discussing a different theorem for 5.1, and then 5.2 we'll be exploring linear transformations. So 5.1 is going to be super brief because all it is this theorem called the matrix inverse theorem. I say all it is, but meaning it actually is a very important thing, but it's just like, now you know this. There's not a lot of questions that can be asked about like your understanding of it besides like implicitly in other questions. But the matrix inverse theorem. So the matrix inverse theorem is a kind of summation of everything we talked about, how everything is related. So if you remember in week 3, when we talked about determinants, we said, okay, if something has a non-zero determinant, it means it's invertible, it means a reduced or echelon form is the identity, it means it has a zero kernel, it means it's all these things. Now we have even more, and we're going to formalize it to something called the matrix inverse theorem. These are all the things we've talked about so far that apply in this class. The matrix inverse theorem has a lot more things that are defined by it. There's other math classes, like when I took Math 312 at Penn, we had like 20 different components of the matrix inverse theorem. So these are just the important ones to know for this class, but just know that it's a very important thing that kind of relates everything we know. So essentially what we're saying is the matrix inverse theorem, so if it has an inverse, we also know all of these things. So let's talk about what we've seen before. We've seen that the reduced echelon form must be the identity, right? We know that because for it to exist, the inverse to exist, we would have to find the reduced echelon form to be the identity on the left to make what was the identity on the right become the inverse. Again, that also means that determinant is not going to be equal to 0 because we know that when we do this, the determinant is always like equal to the product of the diagonal, essentially, and all of this is just connected. This allows us to bring in the idea of the rank nullity theorem, right? So the rank is going to be equal to n because this means for the reduced echelon form to be the identity, that means that each variable is going to be a pivot variable. So the rank is going to be equal to the number of variables, so that's the number of columns. So rank is n, therefore because rank plus nullity is equal to the number of columns, the nullity is going to be 0. This also tells us that the columns and the rows are, I guess I'll do it here in color for what's kind of newer, that the nullity is going to be equal to 0. The columns and the rows are linearly independent. So this makes sense because if you remember how we check for linear independence, we check to see if we have essentially a pivot variable in every variable. Like if we have, even if it's a non-square matrix, we check to see if the only solution is the trivial solution, because when the only solution is a trivial solution, that means there's no way to combine the columns in a way to make each other. And so this follows that the columns and the rows are all linearly independent. We could have connected this a little bit sooner, I guess, but the fact this also tells us that AX equals B has unique solutions. So this, because the reduced echelon form is the identity matrix, it's going to equal every single value in B. It's not going to have no solutions, because remember the stipulation for no solutions is that it has zeros in one row in A and then something non-zero in B. But in this case, we know that the reduced or echelon form is the identity, so there's always going to be a 1 along the diagonal. Something always going to be equal to it. So X equals B has unique solutions, therefore X equals 0 only has a trivial solution. That goes in hand with the fact that the nullity is equal to 0. These two are essentially mean the exact same thing. And then kind of going along the lines of that, the column space and the row space both span Rn. So for an n by n matrix, so for example, for like a 3 by 3, you will have your columns, you will have, in your rows, you'll have 3 by 1 linearly independent columns / rows, which allow us to span R3 either way. So for the column space, we have 3 linearly independent columns, span Rn, row space, same thing, span Rn. This then follows that the null space is empty, right? There's no, it only has the trivial solution, it has a nullity of 0, the null space is empty. That's the matrix inverse theorem, it's kind of just everything coming together. So we'll do a few practice problems, but there's not really much practice that can be done with this besides just like solving for rank and everything. So here's an example. Using the matrix inverse theorem, determine whether the matrix is invertible just for your answer. This one's a quick and easy one. So looking at this matrix, we know that this matrix is invertible because it's upper triangular. And the determinant of an upper triangular matrix is the product of its diagonal. So 1 times 1 times 1 is 1, which means it's not equal to 0. So the determinant is not equal to 0. Therefore, it has an inverse. If A is invertible, compute the inverse of A, denoted as A to the negative 1. We can compute the inverse of this by augmenting it with the identity matrix. 1, 0, 0, 2, 1, 0, 3, 4, 1, augment 1, 0, 0, 0, 1, 0, 0, 0, 1. This one's pretty quick because we only have to get rid of 3 things. But I also guess this is a good time to note that the inverse of an upper triangular matrix is going to be an upper triangular matrix. The inverse of a lower triangular matrix is going to be a lower triangular matrix. So here we know we're looking for the inverse to be upper triangular. Let's do row 2 is equal to row 2 minus 4 row 3 to get rid of this row here, this 4 here. So row 1 and row 3 don't change. 1, 0, 0, 1, 0, 0, 1 here, 0, 2, this goes to 0, 0 minus 0, 1 minus 0, and then 0 minus, so this becomes negative 4. And then let's do row 1 is equal to row 1 minus 3 row 3 to get rid of the 3. 1, 0, 1, 0, 0, 0, 1, 0, 1, negative 4, 0, 0, 1. It's gonna be 1, it's gonna be a 2, 0, 1, 0, negative 3. And then just doing one more to get rid of this 2. R1 is equal to R1 minus 2 row 2. 0, 0, 0, 0, 1. 1, negative 4, 0, 0, 1. 1, 0, 0, 1 minus 0. 0 minus 2 times negative 1, so negative 2. And then negative 3 minus 2 times negative 4, so negative 3 plus 8 is 5. And that's it. That's the inverse of this matrix, which is also going to be an upper triangular matrix. Yeah, so we know all this because the determinant is not equal to 0. The last thing is they want us to verify your result by showing that A times its inverse is equal to the identity matrix. So we know that's going to be true. So we know 1, 0, 0, 2, 1, 0. So this is A times its inverse, 5, 0, 1, negative 4, 0, 0, 1. We know that this product is going to be equal to the identity matrix, but we can verify it for funsies. Row times column, so row plus 2, 1 plus 3, 0, 1, 5 plus 2, negative 4 plus 3, 1. Row 1 plus 0 plus 4, 0, 0, negative 2 plus 1. 0, 0, 5 plus 1, negative 4 plus 4, 1. And then lastly, 0 times 1 plus 0 times 0 plus 0 times 1 times 0. 0 times negative 2 plus 0 times 1 plus 1 times 0. 0 times 5 plus 0 times negative 4 plus 1 times 1. And then we can look at this all together, and everything that's not along the diagonal becomes zeros. So we see that the product of A times its inverse is equal to the identity matrix. Moving on to the worksheet questions, which are also pretty brief because there's not much to do with matrix inverse theorem question-wise directly. This is asking us what the rank and nullity of A is. We want to find the reduced or echelon form of A. And this one is quite obvious because every row is a multiple of each other. And so when that happens, we know that we could just cancel all of those rows out by doing like for this example, like row 5 is equal to row 5 minus row 1. Row 4 is equal to row 4 minus 2 times row 1. So then the reduced row echelon form looks something like this, or it is this, where we have x1 is our pivot variable, and then x2 and x3 are our free variables. And they want to know what are the rank and the nullity of A. Rank is 1, because we have one non-zero row, and then the nullity is equal to 2, because rank plus nullity is equal to number of columns. Okay, let A be a M, okay, let's be distinct about this. Let A be an M by N matrix, and let B be an L by N matrix. How is the kernel of C related to the kernel of A and kernel of B, where we have this? So think, just to give these numbers so we can kind of conceptualize it, let's say this is a 3 times 2, and this is a 2 times 2, I guess, makes it the easiest. So A is an M by N, so 1, 2, 3, 2, this is A, and then B is just 1, 2, 2. So it's a 2 by 2 and a 3 by 3. And we're stacking them on top of each other. So literally, if we were to do this, we put this together, and then we've got 1, 2, 2, 3, 1, 2, 2. So like literally putting them on top of each other. And now this is asking us, how is the kernel of C related to the kernel of A and the kernel of B, where this is true? So essentially, we can look at the fact that whatever it's going to be, if V, so we have AX is equal to 0 and BX is equal to 0. For any of those things to be true, then for whatever belongs to the null space of this, whenever belongs to the null space of this, it must also just belong to the null space of C. Because remember, the basis of the null space is always going to be the same size as the base of the row space. So here we're only talking about, for example, this is like R2, like R2, 2 by 1 vectors. So anything that makes this set AX equals 0 and this set equals 0, then it's going to make CX equals 0. So you can think of the kernel of C being the intersection of the kernel of A and the kernel of B, because it's asking for both of them to be true. What sets both of them equal to 0? So it's the intersection, the and. Cool. The last worksheet question is literally just explicitly asking to justify the rank nullity theorem, not the rank nullity theorem, the matrix inverse theorem. Explain why they are equivalent. So there's a lot of different ways to talk about this. I'm just going to kind of give the response that was given for this worksheet, but just the way that I talked it out and how they're related, that's justification enough. So these imply each other because since the row operations either leave the determinant alone or multiply by a non-zero constant. So when you do these row operations, your determinant is going to not be affected, or it's going to keep its 0 or non-zero-ness. And since the determinant of the identity matrix is 1, so like assuming when you find because this is how we solve for the inverse of a matrix, that means that the determinant of A can be the determinant of I, which is equal to 1 times some consequence of doing row operations with the determinant. That means that it also must be, like, if it's 0, it's going to stay 0, but if it's non-zero, it's going to stay non-zero. If the determinant is not equal to 0, then its reduced row echelon form must be the identity matrix, which we discussed. And since it's upper triangular, or it's just diagonal, and can therefore only have ones along the diagonal. Cool. Well, no, not the greatest explanation, but we've talked about it a bunch. So we can also say that A and C apply each other because what we discussed earlier, so the columns of A generate the columns that generate the space, right? And since we say, because it's invertible, it has full rank. So like we said earlier, when something has full rank, every single column is going to be linearly independent, which goes along with this idea. And they will generate Rn because since it's invertible, the rank is n, so that tells us we have n linearly independent vectors, which will generate Rn. Then like the part E, this equation x equals b has a solution for every b that belongs to Rn because the reducer echelon form is the identity matrix, so it's going to have a one-to-one correspondence with the values of b. So any b that you put into there, it will have a solution. It'll have a unique solution actually. And then lastly, the transpose is invertible, which we know. So if it's invertible, we have that this is true, right? We know this. And then we can take the transpose of each of these expressions, or just this expression, I guess, both of them. When we do the transpose, it switches the order. So when we do that, it's going to become a to the negative t, a to the negative 1 t, a to the t is equal to a to the t, a to the negative 1 t, which is equal to I. We can also take the transpose here, which tells us that AT is invertible with the inverse A is equal to negative 1 transpose. And we also know that A to the t is equal to A. We also get that if A to the t is invertible, then so is A. Essentially, by making this a transpose, and then we're showing that it still holds, like this is the exact same thing that we said up here, but all of them are transposed, then it works out. So yeah, that's 5.1. You don't really need to know, like there's not going to be any questions that are like prove the matrix inverse theorem, anything like that, but just having the idea of what is involved in the matrix inverse theorem is going to actually just help you. So this is a very beneficial section of this class. It's not too stressful, and it's just going to provide you more weapons and tools for solving problems. So that's 5.1.